There are places in the universe so strange, so violent, and so alien, they defy everything we think we understand about light, matter, and time. At the heart of nearly every galaxy, including our own Milky Way, lurks a gravitational monster, a supermassive black hole that devours anything that dares stray too close. But despite their cosmic size and power, these celestial beasts have always hidden behind an inescapable veil of darkness, until now. In a breakthrough that feels like seeing through the fabric of space-time itself, astronomers with the Event Horizon Telescope (EHT) collaboration have just demonstrated a technique that could soon let us capture black holes not just in blurry shades of radio intensity, but in vivid, multicolored detail. Published in the Astrophysical Journal in May 2025, this pioneering work redefines how we observe the most mysterious objects in the universe and could unlock secrets we've only dreamed of glimpsing. Let's step into this new frontier. Color is more than what we see. It's physics, pure frequency, a fundamental property of electromagnetic radiation. Red light has long wavelengths, stretching lazily through space like ripples across a still pond. Blue light is the opposite. Tight, high-frequency pulses packed with energy, like pebbles skipping rapidly across the surface. Every color you've ever seen is a frequency written in photons, but the human eye only captures a narrow slice of the electromagnetic spectrum. Our retinas, equipped with cones sensitive to red, green, and blue light, feed signals to the brain, which blends them into the full rainbow we perceive. Digital cameras imitate this. They use color filters and sensor arrays to capture red, green, and blue, then reconstruct what we interpret as a color image. Yet the cosmos emits far more than visible light. Beyond the rainbow lie realms of infrared, ultraviolet, X-ray, gamma ray, and radio waves. We can't see them, but they carry some of the most important messages the universe sends. And in that invisible ocean, black holes whisper. Radio telescopes are among the most powerful tools we have to decode those whispers. They detect radio waves, enormous compared to visible light, that can pass through gas, dust, and magnetic fields without scattering. This allows astronomers to peer into regions where optical telescopes fail, such as the center of galaxies or the regions immediately surrounding a black hole. The history of radio astronomy itself is a testament to the ingenuity of scientists working with the invisible. It began in the 1930s with Carl Jansky, who accidentally discovered radio waves from the center of the Milky Way while investigating static that interfered with telephone calls. Since then, radio telescopes have grown from simple antennas to vast international networks capable of functioning as a single Earth-sized instrument. But here's where the artistry comes in. Just like visible light has colors, radio waves have frequencies. These frequencies are organized into bands, and each band reveals something different about an astronomical object, like layers of an onion or tracks on a symphony recording. Most radio telescopes, however, are limited. They can typically only observe one frequency band at a time. To build a color radio image, scientists must take multiple snapshots at different times, each in a different frequency. It's a bit like photographing a sunset through a keyhole, one color at a time. If the scene changes between shots, if a star flares, or matter falls into a black hole, the final image becomes distorted or useless. Timing is everything. This is where frequency phase transfer, or FPT, enters the stage. Imagine trying to take a photo on a windy day with a shaking camera. The image will blur, unless you can stabilize the lens. That's what Earth's atmosphere does to radio signals. It introduces noise and distortion, especially at shorter wavelengths like 1 millimeter, which are essential for high-resolution imaging. The atmosphere acts like turbulent glass. But at slightly longer wavelengths, like 3 millimeters, that turbulence has less impact. FPT takes advantage of this by using stable 3 mm observations to calibrate and correct simultaneous 1 mm data. The technique is similar in principle to adaptive optics in visual telescopes, which use laser beams to track atmospheric disturbance and correct the image in real time. By combining both wavelengths during the same observation window, the team corrects for atmospheric distortion on the fly. The result is a crystal-clear image that would otherwise be smeared beyond recognition. This technique, still in early demonstration, is a major leap forward for very long baseline interferometry, VLBI, the method that makes the EHT function like a telescope the size of Earth. By improving clarity and enabling simultaneous multiband observations, FPT may soon become an essential component of next-generation radio astronomy. The EHT collaboration demonstrated this technique using telescopes in the Global Millimeter VLBI Array, GMVA, successfully observing known astronomical sources in multiple bands at once. Their results showed that FPT not only works, it works with remarkable precision, even at the challenging high frequencies required to study black holes. And that's just the technical side. The human side is just as compelling. Behind the scenes of this breakthrough lies one of the most globally distributed scientific collaborations in history. More than 300 researchers across over 60 institutions worked in sync, coordinating time zones, equipment schedules, and weather patterns across Earth's highest observatories. From the Atacama Desert in Chile to the icy summit of Mauna Kea in Hawaii, these sites all contribute to the EHT's vast planetary vision. This isn't just a telescope, it's a chorus of continents. This development isn't just about increasing clarity. It unlocks entirely new dimensions of observation. Because each radio frequency penetrates different parts of a black hole's environment, a multicolor radio image becomes a multi-layered map. One frequency may trace the cooler outer regions of a swirling accretion disk. Another may highlight jets of plasma moving near light speed. Yet another could reveal the dynamic chaos near the event horizon, the very edge of where space collapses into singularity. We're not just seeing black holes, we're dissecting them layer by layer. We're peeling back the surface of phenomena long considered fundamentally unknowable. And this is just the beginning. The upcoming next-generation event, Horizon Telescope, NGEHT, will use a larger, more sensitive global array to record not just snapshots, but videos of black hole environments, possibly dozens of frames per second. When combined with FPT, this means we could witness magnetic fields twisting, gas spiraling inward, and relativistic jets bursting outward in a kaleidoscope of radio colors. A literal movie of matter falling into nothingness. Meanwhile, the Black Hole Explorer, BHX, a proposed space-based mission, could eliminate atmospheric interference entirely. From orbit, radio telescopes could operate with stability and precision unmatched on Earth, using FPT to its full potential. These missions may one day merge real-time imaging, multiband color, and time-resolved motion into a single feed, a live stream of black hole dynamics across space and time. It's a technological leap that echoes the discovery of X-rays or the launch of the Hubble Space Telescope. A new sense, a new way of being present in the universe. But even more than that, it's a new language of vision. For generations, we've relied on visible light to shape our view of the cosmos. Now we're expanding that vision into realms our ancestors never imagined. We're giving shape and structure to the invisible. We're turning theory into observation, math into motion, shadow into symphony. We're learning to see without eyes. Think of what this means. For over a century, black holes have loomed in scientific imagination as monsters, theoretical, untouchable, incomprehensible. From Einstein's equations in 1915 to the first image of a black hole in 2019, we've inched closer to visualizing the unseeable. But now, in 2025, we are preparing to see them not just as shadows, but as symphonies of frequency, as dynamic, evolving structures of space and time. as paintings written in plasma, gravity, and color. We're on the cusp of seeing the invisible. Soon, the darkest objects in the cosmos will be revealed in hues that speak of energy, structure, and time itself. So if you're fascinated by space, time, and the frontiers of science, hit that subscribe button, because the day is fast approaching when a black hole won't just be a ring of fire on a silent background, but a living, breathing storm of color dancing on the edge of eternity.